And then we go to our next speaker, Lisandro Jimenez. He did his bachelor in civil engineering and a master in structural engineering at the Universidad de Laval in Colombia, and did his professional doctorate in construction engineering at University of Twente. And he's currently a PhD student in computer science in the formal methods and tools group at the University of Twente. So he comes from the engineering perspective, and he will talk about today about the system level prognostics for management of complex assets and opportunities and challenges which can be seen there. So Lisandro, the screen is yours.
Thank you very much. Can you hear me?
Yes.
Excellent. So thanks for the introduction, Matthias. Yes, I'm Lisandro Jimenez, and in this presentation, I'm going to show what is my research about and some results that I have obtained so far. I think it's also important to introduce my group of supervisors, which is composed by Professor Mariela Stulinja, Professor Tito Tinja, and Professor Tom Heskes. Before starting the presentation, I would like to say some things about me. I come from Colombia, from the capital of salsa, Santiago de Cali. So for European standards, I'm a good dancer, but for Latin American standards, I'm not. In my free time, I like to spend, I like to do some sports. I really like body pump. I think it's a nice exercise, and yeah, there's always nice music. Matthias already mentioned this part, so I'm just going to jump it. But yeah, basically, currently I'm working my PhD, which is funded by the Primavera project, and my PhD is about system-level prognostics of complex engineering systems. So to start, I think a fair question will be, what is prognostics? It is in the title of the presentation. So quickly, for those of you that don't know what prognostics is, well, I think this is a nice picture that can represent what that is. It's basically a prognosticator using a tool that tries to foresee an event of interest in the future. A more scientific or ad hoc definition in predictive maintenance would be the one that you see on the screen, where basically prognostics would take care of predicting failures that are going to happen in the future based on the current state and foreseeing operational conditions of the system. Why prognostics? Well, I think it's quite intuitive that if you can see what is going to happen with your system in the future, you can make a better investment of your resources. And you're trying to reduce costs, etc. And how to carry out prognostics? Well, we don't use witch balls. What we do is to use mathematical models like data-driven models, physics-based models, knowledge-based, and hybrids. I'm not going to elaborate on this type of models. If you are interested to know more about them, I recommend the reference that you see on the screen. There, the authors make a distinction between the models, that they compare it, what are their strengths and weaknesses, and future research lines. Now, a little bit about system-level prognostics. Well, first of all, what is a complex system? It's a system that has several interacting components. And often these kind of systems are modeled with graphical models like Bayesian networks. And some aspects to know about system-level prognostics is that it takes care about relationships between failures, which is something that is more in the area of dependability analysis, and that consider system dependencies. There are different types of dependencies, like structural, economic, stochastic, among others. And common approaches, as I mentioned before, is with graph models. There are several of them, just to mention. Some are Bayesian networks, fault trees, and more recently, graph neural networks, which is an approach that is more in line with deep learning. If you would like to know more about that, I recommend the reference that you see on the screen, where the authors use this type of novel technique in order to use it to create system-level prognostic models. Now, the content of this presentation, I'm going to talk about some main challenges in system-level prognostics. I will go in details in my research, especially in topics in model learning and survival analysis. And I will also talk about some future work. So to talk about some of the main challenges in system level prognostics, first let me quickly present an overview of the process that we are interested about. So we have prognostic metrics, which is basically what we want to obtain from the model. A very popular prognostic metric is the remaining useful lifetime, but please be aware there are more metrics a part of the RUL. If you want to know more about that, in the reference that you see on the screen, the authors provide a more comprehensive overview of all the prognostic metrics that exist. These metrics are obtained from system level models, which we want to connect them with the real world, in this case with real world information or data. And often this connection cannot be done directly, so we need somehow to have some interfaces. And I think it's, you might expect that there are different challenges in each of those aspects. So for instance, in real world data, one of the challenges is that we have underrepresentative and limited data sets. There are several reasons for this. One of the commons is that one always have limited information about your the failures in your system, but you always wonder whether your data is complete or representative enough. So alternatives for these are data augmentation and fusion, where basically you try to combine different sources of data, and transfer learning, where you try to reuse, for instance, pre-trained models in other similar systems. Regarding the interface, the challenge is that there's a weak link between probability risk analysis and reliability models. A way to address this issue could be by means of survival analysis. This is for me a fairly new topic. So actually, if people have more insights in this regard, please share with me. I would really appreciate it. And other challenges regarding the models, just to mention a couple of them, is that there is an ineffective modeling of the interactions. Why? Well, not always you know how are all the dependencies in your system, and also what is going to be the effect of maintenance strategies in your prognostic analysis. So it's difficult to generalize this type of models, especially if they are based on physics. This can be quite challenging. So alternatives for these are in model learning and dependability and modeling analysis. If you would like to know more in detail what are the gaps in system level prognostics, I recommend to go to the literature that I'm presenting in the slides. But by now, I'm just going to focus the remaining part of this presentation in my research, highlighting a couple of aspects, which is contributions in model learning and survival analysis. So about my research, let me first talk about this first paper that I made. Is for a conference that is going to take place in 3 weeks in France in the Israel 2021. And in this paper, what we did was to compare tree graph models like fault trees, decision trees, and binary decision diagrams. And we wanted to understand how do these models compare. And the contribution of this paper is that we use a running example that allow us to exemplify how these models perform and easy the comparison and see how similar and different they are. This is my recent paper, which is about automatic inference of fault trees via multi-objective optimization algorithms. Here, the task is that based on a data set, we want to obtain automatically a fault tree model. And we use this by multi-objective optimization algorithms. So the contributions of this paper are mainly that we introduce the concept of multi-objective optimization. This is important to notice that this problem was already addressed before in another research using genetic algorithms. But the difference with our paper is that in this case, we're extending the analysis in a multidimensional space. We also harness information based on minimal cut sets in our objective function, and we carry out a thorough parametric analysis. So I'm going to show a few details about this paper. Unfortunately, I cannot go too much in depth. So basically, these are the metrics that we were optimizing. The first one is an accuracy that is computed based on data. And this was basically the only aspect that was considered in the previous research that was conducted by Linard in 2019. But we introduced other parameters such as the size of the tree, because we want to also consider small full tree structures, and error based on minimal cut sets, which in this case, this is based on the RV coefficient, which is an extension of the Pearson correlation. And then we applied the elitist non-dominated sorting genetic algorithms and crowding distance. As I said before, I cannot give details on these. If someone is interested, please just let me know. I will be happy to give more details about that. But these are some results. Some of the results we have, I think the most interesting one, I can point it out. Let me just see if I can use the laser. Well, our model or algorithm managed to, let's say, better achieve a global optimum solution. And the most interesting result is related to the size of the tree, where we can observe that for our approach, which is the orange lines, our approach always outputs small tree sizes compared to the other approach where, because they were not controlling this aspect, the models can get big. And well, that makes more difficult the interpretation and handling of the model. And of course, this aspect has influence on the convergence time. So in this case, our algorithm is faster because it's also considering just, let's say, higher quality and small trees, full trees. So an example of the output of the model. So this is the COVID-19 fall tree, which you can find in this reference. And I know that you cannot read the details of this fall tree, no worries. I just want to show how big and complex the model is. But after applying our algorithm, yeah, we use a process in order to, part of our methodology was to use a Monte Carlo method based on this fall tree, generate a data set. And then what we wanted to do is from that data set, return to this fall tree. And we output this fall tree that you see here on the right, which is clearly smaller, but they both are equivalent. Now, what's next? We plan to extend some results of this research. I'm going to work on this together, my colleague, Matthias Volk. And we want to evaluate more aspects such as incompleteness in the data set. So how to handle that, how to harness symmetry. So for instance, if you see the picture in the back, this is an example of a symmetric system. We have a bridge, which in this case has a symmetric property. So how could you use this kind of properties in order to, for instance, make a faster way of finding the optimal fall tree? And also how to handle noise in data. And now to, the last part of this presentation is regarding another aspect that I've been busy with is online survival analysis for time to damage prediction. I'm using a data set from the city of Breda. So this is one of my case studies. And the system of interest are water and sewer pipe networks. Now, to just give an overview of what's the research problem here, I need to introduce the concept of survival analysis. It's a branch of statistics. And basically, what we want to do is to compute the time until the occurrence of an event. So just to clarify that, let me give you an example. So we need an exposure event which determines when your clock starts. Then you have an event which determines when your clock stops. And whatever is the time in between, that's the survival time. Examples, the exposure could be a marriage and the divorce could be the event. And then the survival time will be, well, how long the relationship lasts. Or you can have another example when the component is manufactured and the component is failed, then that time that takes to occur, that is the survival time. So for our case, we are trying to have water and sewer pipe manufacture, and we have damages in this data set. We have different type of damages, and what you're seeing in the screen are the codes associated to these damages. And we have, for instance, soil deformation, cracks, etc. And we want to compute what is the survival time given those features. So just to give an example of that, features like age of the pipe, material, geometry, the severity of the damage, the function of the pipe, among others. And we want to compute results such as this one, which are survival curves. This is the Kaplan-Meier curve, which is a non-parametric curve, which you can build based on the data. And this is just an example. These are some early results. As you can see here, basically what is exemplifying this curve is that we have the age of the pipe, we have the survival curve, where 1 means your pipe is going to be perfectly fine, it's 100% reliable. But then, as you can imagine, over the time, if no maintenance is performed, well, you tend to start having more failures in the pipes. And then one question will be, okay, how this curve will look if we start considering more features. So for instance, if we start paying attention just to sewer pipes made out of concrete, then we see the blue line, and we see that the slightly shift compared to the other one that was not making any discrimination. And if we keep adding more features, so for instance, how this curve will look if it's a sewer pipe made out of concrete with an oval shape, you obtain another curve. So that's basically the concept behind this research. And that's why it's called online survival analysis, because we want to provide these features that can be updated, these kind of reliability curves. And this is very important because then you can have more updated results in your prognostic metrics. That was it from my side. Thanks a lot for your attention. I omit several details, so you can ask later. And in case, also you can send me an email. That's my email address. So we can also maybe discuss that in other ways. But thank you very much.